Oh, you like the music, Ronnie? It's Vivaldi, Four Seasons, in case you're wondering. Yeah. Oops. Something about the music you were playing right before this, Dr. Drews, reminded me of like Tiny Toons or Looney Tunes. Does that composer write for those cartoons? Yeah, because I could have swore I've heard that one before, like somewhere in my childhood, and I want to assume that it was like a Looney Tunes thing or maybe some video game. I don't know, but I know I've heard that one before. Okay. Um, so it's 3 o'clock now. I'll go ahead and get started. Before I go into the lecture today, though, just a couple things. Oh, let me stop the music. Yes, it is a beautiful day to be alive. Well, although I'd rather be alive, pre-quarantine, but I guess I'm okay with it for now. Okay, the music should have stopped. So quick note before um, we go into the lecture here. Office hours are going to change for me. They're going to change in a way that they become more open. So if you are still good with Tuesday, Thursday, then that's totally fine. But the only thing I wanted to mention right here is that I'm going to be available for appointments, um, similar to how Dr. Drews is. However, the sort of one difference here is that I have a weekly schedule that changes quite frequently because I do private tutoring for high school students. And so what that means is that you basically just send me an email and I'll find a time individually with you to meet. But my Tuesday, like I said, my Tuesday, Thursday office hours will still be open to everybody. Um, and if you have like specific questions, feel free to email me and we can set aside like half an hour. Most days I am free, and most of the time I am free between like 9 and 9, pretty much. But you know, within a given day, maybe there's like 2 or 3 hours where I won't be free because I'm tutoring. So, um, but yeah, if you're interested in that, feel free to email me. I've had a couple students already request it, and so I've already set up a couple appointments, and I might as well figure I open it up to everybody. Okay, so for our topic today, we're going to be talking about um, multiple steady states in CSTRs, and Dr. Drews kind of mentioned this at the end of the last lecture, but I just really quickly wanted to brief recap the sort of general idea here and why we're interested in this. So here the idea is that within a given system, a given set of reactions, a given set of operating conditions such as reactor temperature, volume, inlets, and the heat exchanger utility, like utility temperature, and the UA values. Assuming all of these values within a given reactor are consistent, um, you would expect that you could get a particular conversion rate out and thereby get a particular outlet stream. However, in systems that have multiple steady states, you realize that, so maybe for this particular system, we get a low conversion. Given the exact same system, you could potentially get a much higher conversion rate, even though everything else, all operating conditions are completely identical. And we're sort of, this is generally the idea, like, you know, if you're, depending on what your system is, mainly what your reaction is, you could potentially have steady states that allow for different conversion rates, in spite of the fact that all of the system operation variables are the same. And so, you know, given a particular set of operating variables, you could either get, you know, a 3% conversion rate, which was really low, or, you know, upwards of like a 90%, depending on what your system is looking at. And so we're going to be looking at that today, and it's actually pretty important to, you know, efficient operation. So hopefully you'll all remember how to do this when you get a job. Okay, so the way that before we start this, I'm going to first sort of reintroduce the energy balance, and then we're going to sort of play around with the variables to get it into a working form for our systems. And so the energy balance is written as 0 is equal to the summation of I to Z and I naught CPI times T minus T naught plus V times the summation for all, whoops, for all reactions. I'll call that, I guess, 1 to Q. Rj delta Hj minus Q minus work shaft. However, in all of our cases, work shaft is going to be 0. So we'll just drop that off at the beginning. Now, before we do this sort of rearrangement that I'm talking about, very briefly, I'm going to sort of discuss what these terms are and sort of show you why we're separating it the way we are. So this first term here is going to, sort of by definition of what it is, it's the molar flow rates times their heat capacity times delta T. This essentially is an energy change due to the flow rates of material, so like the reactants and the products. Oh, yeah, sorry. I always forget to put the little caps on the V. Yeah, that would be volume. So yeah, this is energy change due to molar flow rates of reactants and products. Reactants and products. This middle term here with the summation is energy change due to the reaction itself. So, you know, if a system is exothermic, for example, it'll release heat. If a reaction, excuse me, is endothermic, it'll absorb heat. And hence, this is why this is the term with the reaction rate. And then this last term, as we learned a few lectures ago, this is Q as defined as UA times TU minus T. This is simply the amount of energy change due to the heat exchanger. Okay, so given that this is the case, and given that this middle term here is sort of like the only one that will generate heat in the presence of an exothermic reaction at least, we can separate that term to the left side of our equation and write it such as negative V is equal to or negative V times the summation of Rj delta Hj is equal to the summation of the other terms on the right side of the equation minus Q. And then we'll group both of these terms, or both of these sides rather, into two distinct variables that we'll simply call G of T, which stands for generation as a function of temperature, and or so energy generated as a function of temperature, and the right side would be energy removed as a function of temperature. So G of T and R of T. And so we simplify our energy balance into simply G of T is equal to R of T. And like I said, the reason that we do this is simply to have a more usable form um, for what we're going to be doing today, which is, again, multiple steady states. So now, from here, I'm going to introduce, or at least sort of lay out the example that we're going to be doing. This is going to be an example of multiple steady states and how we can determine sort of where those are. Irreversible. At what operating temperatures they would be at, and what kind of conversions we can get at those given operating conditions. So given an irreversible exothermic liquid phase reaction, A goes to B. And A is fed into a CSTR with equimolar inert I. And then given, so I'm going to write out a bunch of parameters that would be given in this problem. So it's quite a few of them. Oops. And given Na naught is equal to 80 moles per minute, CPA is equal to 20 cows per mole degree C, which is also equal to CPB. And then CPI for the inert is equal to 30 cows moles per minute. Oh, excuse me, moles per degree C. Tau, our residence time, is equal to 100 minutes. Delta H is equal to negative 7,500. TU is equal to 300K. UA is equal to 8,000 cows per minute degree C. K is equal to 6.6 times 10 to the negative 3, and units are 1 over minute. This is at 350K. And then E is equal to 40,000 cows per mole K. So question, units of delta H, did I not write that? I did not. Units of delta H are going to be cows per mole. Thank you. Okay, so part A of this is sort of going to be a review-ish of what Dr. Drews did last time, which is to write XA as a function of the reactor temperature T. Now, I say that this is kind of a review, but we're also going to be sort of incorporating it into today, because what this part is going to be using is the form of the material balance that Dr. Drews introduced on Wednesday, and then later down we're going to be incorporating the energy balance. So starting from equation 5.8, which we introduced on Wednesday, we know that V is equal to Na naught times XA over negative RA. Here, I didn't write it up there, but we can assume elementary. assume elementary. And so based on that, we can say then that R is equal to KCA, and RA would then, of course, be negative KCA. Now, we could also, in order to write this as a, to write XA as a function of temperature, we can write RA by putting, plugging in CA, CA is equal to CA naught times 1 minus XA. Now doing that, we can derive a new expression here, which is that RA is equal to negative K CA naught times 1 minus XA. So if we plug that into our material balance, we're going to get Na naught times XA over KCA naught times 1 minus XA. The negatives here will cancel out, so it should remain positive if I did that correctly, which I'm fairly certain I did. And then I'm not going to show all the algebra for these next steps, but it's fairly straightforward. We're just going to rearrange the entire equation in order to solve for XA. And then I'm going to write down a couple substitutions that you need to make in order to get the form that I'm going to be using. So we're going to do a substitution for CA naught, which is going to be equal to Na naught over nu naught. That's the molar flow rate. And then another substitution would be tau is equal to the volume divided by the same flow rate, nu naught. So using these substitutions and a rearrangement of that equation, algebraically, we can get that XA is equal to tau times K divided by 1 plus tau times K. Now, recall that the question was asking us to write, the question was asking us to write XA as a function of T. And here, our variable T comes into the form of K, because as you recall, K itself is a function of T. So I'll put putting that there to remind us of that. And now we're being asked to, so we weren't given a inlet temperature here, or sorry, a reactor temperature, because this T is a variable. It wasn't given in the problem. And what that means then is that our function K, assuming it wasn't, it's not operated at the temperature or the value of K that was given, which was 350 K. Our K in this case, K of T, is going to be equal to our original K, which is, I'm going to mark as K1. So let me go back and redo that. This here, I'm going to start labeling it as K1 because that was our K given at a particular temperature. So to calculate a new K, we go to our equation here, which is going to be K1 times the activation energy divided by R times 1 over T1 minus 1 over T, our reactor temperature T. And so plugging this into XA, we get a rather lengthy equation that I'm going to just copy and paste because I don't want to write it. So it'll be K times, excuse me, tau times K divided by 1 plus tau, and then the same thing on the bottom there. So this is our expression of XA as a function of temperature. Oh, yeah, sorry. There is a exponent here. Actually, let me just shift everything over because that's kind of important. Let's back up. So K1 exponent T1. 1 plus tau. I guess I'll just rewrite it because it's easier. Exponent of EA over R times 1 over T1 minus 1 over T. So there is an exponent right there that I forgot to write. Sorry about that. For the equations for V, that K is K1, right? The equation V, this is, technically this is just going to be K at whatever our operating temperature is. So in this case, if I wanted to label it, I can write it as K2 or just K. It's separate from K1. It would only be K1 in the case of running the system at 350K. All right, no problem. Okay, so sorry about that, but moving on. Here again, we have our XA, and in this case, we actually know every variable in the problem. We were given K, we're given K1, EA, R. The only variable we don't know is, T1 was the 350K. The only variable we don't know is T here, which is our operating reactor temperature. And so the second part of this problem, part B, is find the operating temperature T given T naught, meaning our inlet temperature, is equal to 450K. By the way, Dr. Drew's a neat little trick I learned about this program. If you write a line to extend the page from on the page, you have to erase it. But if I extend the line from the gray area off the page, I don't. Useful trick to extend it quickly. Yeah, that is dope. Okay, so now in order to find T, given our inlet temperature, we're going to have to look to our energy balance. Everything that we did previously was purely in the material balance. So now if we're looking at our energy balance, we know that in our sort of simplified form, not really simplified, but just sort of reoriented, we have the equation G of T is equal to R of T. And in this case, what I'm going to do is I'm going to sort of separate the equations and solve them sort of distinctly. Here, G of T was equal to negative V summation Rj delta Hj. And then R of T was equal to the summation of Ni naught C, well, that's a weird knot, it's too big. Ni naught Cpi times T minus T naught. So there's our T naught coming into the equation, minus Q. And so starting with the generation terms, this is relatively simple because here we can just plug in the material balance that we had in the first part for V. And so we can plug in that V is equal to Na naught XA over Ra naught, or excuse me, negative Ra. And plugging that in here, we get the two negatives will cancel, and so we'll get Na naught times XA over, well, actually, I'll just leave the negative in there for now. Times, in this case, we only have one reaction, so we can take away the summation term, Rj, or just R in this case, and then delta H. So in this case, if we recall that R is equal to negative Ra, this term with the negative and the R will cancel. And so we're still left with the negative outside, which is going to give us negative Na naught XA delta H. Now in this case, almost every term in here is known. So we have delta H is known. It was just given in the problem. Na naught was also given in the problem. And then in part A, we determined XA as a function of temperature. So we know the form of the equation. Oops. We know the form of the equation, but this is just a function of temperature. which again is what we're solving for in this case. So this means that we're pretty much done with this equation. Now this equation, RT on the right, you don't have to do what I'm about to do, but I prefer to do this. So question, shouldn't it be positive? If you're referring to the G equation, the negative still remains on the outside because there is a negative RA here. Negative RA is equal to R, so that's how you can get this cancellation. And then, which means then the negative on the outside of the parentheses remains. Yep, no problem. So in the removal term, what I'm, like I was saying, what I'm about to do is I'm going to do a rearrangement of this equation simply to get sort of an what I think is a nicer form. You don't have to do this, but I think it's helpful. So first thing I'm going to do is we're going to plug in for Q. And when we do that, we simply get UA times TU, the utility temperature, minus T. And then what I'm going to do is I'm going to split up this sum here into two different sums. So this is going to be equal to the summation of Ni naught CPI times T plus, or minus actually, minus the summation of Ni naught CPI times T naught. So all I did was carry this summation term to each of those and split up the sum. And then minus UA, I'm going to do the same thing for the UA term. So the UA times TU and the UA times T. TU, and then plus, if I'm not mistaken. Yeah, plus UA times T. And then from there, I'm going to just, the reason I did that is so I could combine these terms that have the T, because there's a T appears in the UA term and in the summation. So now I can combine those and group them together and get the summation of Ni naught times, oops, Ni naught times CPI plus UA times T minus the summation Ni naught CPI T naught plus UA TU, all this in parentheses. So the negative carried out to the side, in case you were wondering that. And now this, the reason why I did that and I split up the sum, it looks a little bit messier, but the important reason is that this equation, or at least the form of it, should look familiar to you because, again, R is simply a function of T, which means that this is basically a linear equation, mx plus b, where this term underlined in blue is going to be your y-intercept, and then this term underlined in red is your m value, or your slope. And so one thing too I want to emphasize before I switch to MATLAB to show you how this is solved is that this equation, so we sort of define both the left and right side of the equation. So putting it all together, we get negative Na naught xa, which is a function of t, delta h, is equal to the term on the right, the summation of Na naught CPI plus UA times t minus that other term, summation of Ni naught CPI T naught plus UA TU. Now, again, the only variable in here that we don't know is the T variable that's there and the T variable that exists inside of XA. And so if you wanted to, theoretically, you could algebraically solve for it by hand. You'd have to rearrange the entire equation, so you'd get something of the form t is equal to some giant expression over here. I would not do that if you could avoid it, because it becomes very messy. But every other variable in here we do know. So just to reemphasize that, Na was given, delta H was given, Ni knots for the inerts and species A were given, all the CP values were given, UA was given, and same values over here were given. This should have been, it's a little hard to see, but this is TU, which was given, oh no, sorry, that was T naught, sorry. T naught, which was given, and then all these terms on the right were also given. So we could solve it. It will just be a mess to solve it by hand, which is why we are going to switch to MATLAB here. Okay. Thumbs up if you can see the MATLAB. Okay, perfect. So I'm not gonna go through the step-by-step code because that would take a little bit too long. But it's a very simple setup. I did not use any functions in this because I am simply not as good at MATLAB as I am, say, in Python. But this one is simple enough that you don't really need functions. At least I didn't in this case. And so remember that what we're solving for was the temperature of the reactor given a T naught of 450 K. So T naught I have specified here as 450. Everything else in this section is simply just the given values stated in the problem. T here that I'm plotting between is 250 and 450, and then the various expressions that we solved are down here. So RT, GT, XA, and then there's one for K2 as well. The redefined K at a new temperature. So when we plot this, we get a nice curve here, and you can see that again, what we're basically solving is oh, sorry. Can you see it now? Okay, perfect. So question, is this code going to be posted? I could if you want to, but yeah, if Dr. Drews is okay with it, that would be fine. Okay, so what we're looking at here again is our GT curve and our RT curve, and the intersection of which is going to be the solution to our problem. So at roughly, I think roughly 400. I think if you actually calculate it, it's like 399 point something. But at approximately 400, there's a intersection. So question, why aren't we using fsolve function to find the roots for t? You absolutely could, and I would suggest that you do. This is the only reason I didn't was because I didn't. I mean, that's really, you should though. If you were to plot this, you would basically put the equation g of t minus r of t into root finding form. So g of t minus r of t is equal to 0. And then use fsolve to solve it that way. And so, yeah, in this case, at exactly 450 degrees for an inlet, we'll get the intersection at about 400 degrees. So the other thing I wanted to point out on this curve too is, like I explained earlier, the reason that we rearranged RT into the form that we did was to simply show that it is in fact a linear graph, and we can determine the slope and the intercept rather easily. And so I'm going to switch back to the whiteboard real quick. Okay. Okay, so if we take a closer look at that curve, which you should see now, um, this, like we said already, this interception is basically where we solved the value for t, and that came about from simply if you wanted to use fsolve, you would simply rearrange the equation to be g of t minus r of t is equal to 0 for root finding form. And then for a given t inlet, you could determine that the interception would be approximately 400K. And so this, for that particular inlet, you'll notice that in this case, there's actually only one steady state. Now, given that particular operating condition, however, if we were to shift the T naught a little bit down, you could generate a curve that looked like this, where this T naught is approximately 370K, if I recall correctly. And so what that does is, if we look back to our sort of form of RT here, what we're modifying in that curve is the T naught value, which is changing our what's essentially our y-intercept on the line graph. And so it shifts, as a result of that, we end up shifting this orange line over to the left. And in this case, we actually have 3 points where g of t and r of t intercept. In other words, we have 3 points where we have solutions for this set of equations. Recall that each solution in this case is actually a steady state solution. So even though we had only one inlet operating temperature and all the other values are consistent, we actually have 3 possible steady state solutions here. And the idea here is that because of that, you're going to be getting different XA values for conversion values for each of these. So if we go to, I'm going to show a figure out of Dr. Drew's book. This is going to be figure 5.3, I think. Oops. And so this figure is sort of, I think it's kind of a better demonstration, but we can sort of refer to this figure to determine what's happening. So even though there are 3 steady states in here, they're slightly different in terms of what we would consider their stability. So these steady state points could be considered either stable, unstable, or metastable. And the way that you determine that is if we're looking at this curve over here, for this particular point, say I'm going to mark these as 1, 2, and 3. So for steady state temperature 1, when we look at the, if we were to shift the operating condition slightly to the left or slightly to the right, we end up sort of moving down the curve in this direction. And because the system, remember that g of t is the blue one here and r of t is the orange one. And what they represent is generation and removal of energy. If we were to fall down in this direction on the curve, the generation is greater than the removal of energy, which means that this would result in a shift in temperature basically back to the steady state, because generation is greater than the amount of energy you're removing, so temperature increases. As a result of the temperature increase, you basically end up moving back to the steady state value. If we were to shift to the right side of that point, then in that case, the removal of energy, the orange line here, is higher than the generation of energy, which means that we would fall back down in terms of, let me highlight these. we would fall back down in terms of our position in steady state. So the essentially what would happen is any perturbance to the system, either to the left or right of that particular steady state value, will force a shift back to steady state based on where the generation and removal of energy curves fall. So sort of I think a better demonstration of what that looks like is if this is our point one, basically, because the generation curve, the solid line here, is above the removal of energy curve, which is the dotted line I'll do in blue. A, a shift in the our operating condition, our temperature, to the left will automatically shift our system back to this steady state temperature, and vice versa for the other side. So in such a condition where the operating conditions push us back to steady state, if there's a perturbance in the system, we consider such a point stable. So because it's stable on the left and the right, we would consider it just a stable steady state condition. If the opposite is true, and in such a case where, which would be equivalent to 0.2 on our curve, if we move from, if there's a perturbance that causes a drop in temperature from 0.2, then at that point, the removal of energy is actually greater than the generation. And so we'll end up shifting the entire system down to the next available steady state. Either that the entire system temperature will just drop, or will drop until we get to a steady state, or it'll just basically turn off. So in this case, where we have a perturbance that shifts us away from the nearest steady state value, we would consider this an unstable situation. And so this middle drawing is a sort of a demonstration of what is happening at 0.2. Because on the other side, on the right side of the dot, if we're stepping away from steady state by through an increase in temperature, then on that side of the dot, the generation is greater than our removal of energy, and that'll actually just shift us upwards towards 0.3. And then in the last case, in our case, I don't think this, yeah, our third dot up here is actually would be considered stable, because similar to the first dot, on the left side, generation is greater than removal, which would push us back to steady state if we fell down there. And then moving to the right of this steady state value, removal is greater than generation, which will push us back to steady state. Question, we can decide whether generation or removal is greater by looking at the slope of the line with respect to increase or decrease in temperature. So when you're comparing generation or removal, you're not really looking at the slope. You're looking at just simply the placement of the curve. So or the value of the removal or generation curve. So in this case, for example, on the, I'm gonna actually repaste the graph down, because if I erase it, it actually just erases the entire graph. So for example, if I'm looking at any given vertical line across this graph, I can determine at this particular value whether generation is greater or removal is greater by simply looking at the value of the generation or removal curve. And so at this particular value, generation, the top line, the blue line, is greater than the value of the orange line. Whereas if I were to draw that same vertical line, say, over to the right, the value of the removal is higher than the generation. Does that make sense? Okay. And so in our particular problem, point 0.3, the steady state, is actually identical to point 0.1, the first steady state. And again, that's because the generation is higher than the removal on the left, and removal is higher than generation on the right. And that pushes the system back to the steady state operating condition. However, there is a third case where you could be unstable, considered unstable on one side of your steady state value, and then stable on the other side. And so in such a case, we would consider this metastable. And so here on the left side of this third example, the removal of energy is greater than the generation of energy, which means that there would be a significant drop in temperature as you sort of fell on that side of the steady state curve. And then on the other side, if you were to fall on the right side, then the removal is still greater than the generation, but that'll just push you back down to your sort of steady state value. Okay. So I only have about 5 minutes left here. I think that was all I had to introduce. As far as the code, yeah, I'll see if we could post the code. However, one thing I was thinking about that is that like one of the students pointed out, I didn't use fsolve to plot that graph, so I don't know how useful that would be for students to see. Probably not very. But as far as the equations I used in plotting it, you could find them all in the notes right here. But I think that was all I had to go over. So as always, I'll be hanging around to answer any questions if there are any. And I will be playing some music in the meantime. Yes, classical is the best music. A music taste battle? What if I said country was the best music? So Yang, at the beginning I was announcing let me turn this down. I just made an announcement about my office hours, that I was opening up my office hours to be oh wow, you know what this is, Henry. Good. I was opening up my office hours to be available by appointment. So for now I'm going to be keeping my Tuesday, Thursday office hours between 12:30 and 1:30. But if you had a particular question, like over the weekend or something, you can shoot me an email and we'll schedule a time. If you want to set up a time today, Joseph, you can email me. I have one person that I'm meeting with immediately after lecture, and then after that I'll be free. In fact, actually, I'm trying to figure out a way to schedule this appropriately so anybody can access the office hours, even for like the appointments of individual questions. If you want to uh, just hop into the meeting ID for that I use for my office hours at about um, 4:15 today, 4:15, 4:30, and you can sort of sit in on the call. But it is as of right now, it's specifically for that student who had a question to ask. So, question: if we're at an unstable spot, um, if we're at an unstable spot and we deviate from steady state, the temperature of our system will go kind of wild. Uh, yes. So, depending on sort of which type of unstable spot you're at, either a metastable or an unstable spot. So we'll take this the middle case to be our example here. If you're sitting at if you're sitting at steady state and then something perturbs the system, so like I don't know, a valve doesn't quite close right, and you get a deviation from steady state. Um, if you were to step to the right of our steady state value, you could potentially run into a runaway reactor situation where the temperature would constantly increase. Assuming there wasn't another sort of steady state at a higher temperature, you risk an actual explosion. Whereas if you were to go the other way, you risk basically just shutting off the whole system. Chernobyl, yeah, runaway reactor essentially. So question, how do we get to steady state when starting up the reactor if the steady state is at an unstable spot? So it depends on the situation. I correct me if I'm wrong, Dr. Drews, but because I don't have like practical experience in this area, but I would imagine that you don't typically want to run a system at an unstable steady state. Um, but to answer your question, essentially you would if it's at a if it's a situation where it's unstable on both sides, you would have to just get the operating conditions perfect. Um, yeah, it, you would have to get everything perfect. Whereas, let's say that you were trying to go for a metastable position, then you would simply add, if this situation was what we wanted, we would simply add heat to get to a point where we went above the steady state, and then naturally the system would fall to steady state because of the uh, removal of energy being higher than the generation on the The I suppose that would be the only exception to that rule, Miguel. So for at least for table, I think it was table 2 that in the instructions it said you could copy it. Just I mean, even that you can take a digital copy, but if I guess if you wanted to take a picture with your phone, you probably shouldn't do that. Um, but yeah, yeah, no problem.